Welcome back to Neural Intel. All right, today we're diving deep into Lumine, this brand new AI agent that can get this, master massive open world 3D games in real time. And you know how we do it here? We're going to focus on the nitty gritty, the tech, the engineering hurdles, and what this could actually mean for enterprise use. Okay, so let's start with something every gamer knows, right? 10% attack or 5% crit. You probably made that choice a million times. But for an AI, this is way more than just picking a stat. It's a huge test of its ability to think strategically, to understand the context, all inside this giant, chaotic world. So the big question is, how do you even teach an agent to make a call like that? Right. So, we've all seen AI just crush it in games like Go or StarCraft. Those are closed worlds. The rules are set, the goals are clear, but that's kind of like playing on a neat and tidy game board. The real challenge, the next big frontier for AI, is throwing it into the deep end, these massive, messy, ambiguous open worlds.
Yeah, look at this. An environment like Genshin Impact isn't some tidy little problem. It's a living, breathing world. And for an AI to survive in it, it needs to see and read at the same time. That's multimodal perception. It needs a long-term memory to keep track of quests that can take hours, and it has to have lightning-fast reflexes to actually do stuff. These are the exact core challenges Lumen was built to solve.
Okay, so that's the problem. How in the world do you build an AI that can actually handle all of that? Well, the answer is pretty elegant, actually. It's an architectural approach they call hybrid thinking. It's a lot like how you play a game, right? Think about it. When you're just running across an open field, you're not planning every single footstep. You're kind of on autopilot. You just go. But the second you hit a tricky puzzle or a tough boss, you stop, you take a breath, and you actually think through your strategy. This model does the exact same thing. It can generate this inner monologue to plan out complex stuff, and this is the genius part, it only does it when it has to. That's the secret sauce for keeping it fast enough for real-time play. And this loop here really breaks it down. Step 1, it sees what's happening. Step 2, and this is the crucial part, it decides, do I need to think hard about this, or can I just act? Then it either generates a thought or just goes straight to the action. That one little fork in the road, that think or act decision, is what makes the whole thing so darn efficient. All right, so you can't just flip a switch and create an agent like this. It's a huge multi-stage process. I like to think of it as a recipe, a technical recipe for baking a super smart gaming AI from scratch. And what's the first ingredient? A ton of data. We're talking 2,424 hours of human gameplay. And at this stage, it's not about teaching high-level strategy, not at all. This is just about building the basic, almost instinctual skills. It's learning how to move, how to fight, how to open a chest, all just by watching how the pros do it. So they take all that data and put it through this 3-stage process. First step is pre-training. That's the foundation we just talked about. Then comes instruction following. This is where you teach it to actually follow goals. And finally, you layer on the reasoning, the high-level strategy that pulls it all together. Whoa, okay, in this table, this really puts the sheer scale of this into perspective. Just look at that pre-training stage. Over 19,000 H100 GPU hours. For anyone thinking about deploying something similar, this is a massive takeaway. The lion's share of your compute costs is going to be right there, just building that raw foundational skill. So, great, you've spent all this compute and you've got this monster of a model, 7 billion parameters. But now you have a huge engineering problem, right? How on earth do you get this giant model to respond fast enough for a game that needs a new input every 200 milliseconds? That's 5 times a second. And that brings us perfectly to our neural signal check. Look, for an agent that has to interact with the world in real time, inference speed isn't a nice to have, it is everything. If you're too slow, you're dead. The agent just can't play. So let's get into the engineering magic that actually makes Lumen work. And boom, here are the results. Look at where they started, a baseline latency of over 3 seconds. I mean, that's completely unusable. The game would be over before the AI even made a move. But through a whole bunch of smart optimizations, they absolutely crushed that number down to just 131 milliseconds. That's a 25 times speed up. And that gets them way under that 200 millisecond target. And this wasn't just one magic bullet. This was a full stack attack on the latency problem. They did stuff at the model level like speculative decoding, which is a cool trick where a tiny, fast model basically guesses what the big model is going to say to speed things up. And they went all the way down to the hardware, using things like quantization to make the model smaller and custom CUDA kernels.
It's just a masterclass in how to optimize for inference. Okay, so it's great that it can play one game really well, but that's just interesting. The real sign of a generalist agent, the true test, is whether it can adapt. Can you take this recipe and see if the agent can survive in a totally new, totally different world it's never seen before?
And that's exactly what they did. They dropped Lumine, zero shot, meaning no extra training at all, into a completely different game, Honkai Star Rail. And the mechanics are night and day different. It's turn-based combat, not real-time action. The world is a series of hubs, not one giant open map. We're tucking a huge, huge gap between the two.
And the crazy thing is, it worked. I mean, remarkably well. Even though everything it learned was from a completely different kind of game, its core skills, just basic stuff like moving around and clicking on menus, were general enough that they just transferred. It was able to play well enough to finish the entire first chapter of the new game.
Now, this doesn't mean it's perfect. Far from it. And analyzing where it fails is super revealing. Look at this chart. The biggest chunk of its mistakes, over 40%, comes from something called perceptual misrepresentation. What does that mean? It means the AI is literally not seeing the world correctly. It misinterprets what's on the screen, or it just hallucinates things. And that tells you everything you need to know. Robust, reliable computer vision is still the single biggest bottleneck for these kinds of agents.
And the researchers are totally upfront about this. They lay out the next big engineering challenges pretty clearly. To get to the next level, these things need, well, more and better data for one. They need much smarter long-term memory. They need to be able to learn on the fly with reinforcement learning. And of course, they still need to get even faster.
So this all leads to the really big question, especially for those of us thinking about enterprise applications. Gaming is cool, but could you use this same architecture to automate tasks in other complex 3D software? Think about an agent that could navigate something like AutoCAD or operate machinery inside a digital twin of a factory. The potential there is just absolutely massive.
And that's our technical deep dive on Lumine. It's a really significant step forward for generalist agents. Agents that can see, think, and act inside these messy digital worlds we're all building. To keep up with more explainers like this, you know where to go, neuralintel.org. Thanks for tuning in.